What exactly is mTouch? Well, mTouch is an alternative to mechanical push buttons with some distinct advantages. The system is completely sealed, has no mechanical components that will wear with time, and provides a modern-looking design. More importantly, Microchip offers a royalty-free license along with a multitude of resources to aid in the development of your own mTouch applications. So how exactly do we implement mTouch capacitive touch sensing? If we look at a simplified block diagram of an mTouch system, we can identify some main components. First, we have the touch sensor itself. As the capacitive touch sensing name implies, this sensor will produce a varying capacitance that will interact with a relaxation oscillator circuit. When the capacitance from the sensor changes, for example when touched by a finger, the oscillator's frequency will change. In order to interpret this change in oscillator frequency, a frequency measurement component is required in our system. This component will interface hardware and software to accurately determine if and when a sensor has been touched. So let's take a closer look at each component of our mTouch system. First, touch sensor construction. Recalling the equation for capacitance, we can see that there are a number of variables that could change the capacitance produced by our touch sensors. As we will see, the most important variables that we will be concerned with are area and distance. From this equation, the greater the area, the greater the capacitance. As the distance becomes larger, the capacitance drops. Keep this in mind as we proceed through this presentation. So, how do we build a sensor? We begin with a simple printed circuit board. Constructed of FR4, this type of material will enable us to produce a natural capacitance for our application. A copper pad is next introduced. The shape of this pad is not very important. Therefore, we have the freedom to shape this sensor aesthetically to suit a particular design. However, the area of the pad is very important. The larger the pad, the better the sensitivity, and a sensor touch will be more easily detected by the rest of the system. As you can see in this slide, a natural parasitic capacitance to grounds elsewhere in the system has been introduced. I have labeled these pad capacitance, or CP. Next, a touch surface is applied in the form of either window glass or plexiglass. Other materials could be used as long as the dielectric constant of the material is evaluated for functionality. Typically, it is best to design a thin touch surface. Remember back to the capacitance equation. As distance increases, the capacitance will effectively decrease. Therefore, using a surface that is very thin produces a more sensitive system. A finger touch will add a second capacitance in parallel with the pad's capacitance. The iron in an individual's blood creates strings of capacitors between every surface of their body. So, when someone creates a capacitance by moving his or her hand into close proximity of another conductor, it creates a capacitance essentially coupled to ground. Looking at equivalent circuits, we have the capacitance from the pad alone and then a parallel combination of pad capacitance and the finger capacitance, which add together to form a total sensor capacitance labeled CS. We should mention here that the capacitance introduced by the finger is known to be very small, in the area of 5 to 15 picofarad. Therefore, we will want to ensure that the capacitance created by our pad is small as well to make certain that a touch is sensed. Further information on physical design guidelines can be found in application note number AN1102, referenced at the end of this web seminar. So, we now know how to create a sensor that varies capacitance with the touch from a finger. But how do we use this information to detect a sensor touch? This leads us to our next component in the system, the relaxation oscillator. The RC time constant for a charging capacitor is calculated by multiplying the system's resistance by its capacitance, as shown here. Remember that the RC time constant, represented by the Greek letter tau, is the time it takes to charge a capacitor to about 63% of its supply voltage, and 5 times this time constant is the time to charge the capacitor to within 1% of the supply. The sensor capacitance alone, with no finger introduced, will create a steeper charging time as shown. If a finger is introduced, the capacitance of the system increases, thereby increasing the RC time constant, resulting in a longer charging period. Let's add a few more components to our RC circuit.